So now that we've kind of discussed what the notion of a limit is and kind of how to evaluate it graphically, it's about time that we do actually look at a few properties of limits and how to evaluate limits, given a function. Now, we have quite a few properties over here, and these may seem a bit daunting at first. However, you will come to find that it is actually quite intuitive. So we have the multiplication property, where if you're multiplying two functions and you're taking the limit as x approaches a, then you can consider the separate, or I guess you could say the product of the limits of each function. And then kind of by that, we can also determine that if we're dividing two functions, we can just take the individual limits of their quotient, I suppose you could say. And this is assuming that, in this case, the limit is x approaches a if g of x is not equal to 0, of course. Otherwise, this would fall apart, and then we'd have to kind of go into saying that it doesn't necessarily exist. For multiplication and subtraction, for addition and subtraction, we have another property over here, where you just take the individual sum or difference of the limits of the functions. And when it comes to kind of taking the limit as x approaches a of a function raised to a certain power n, then we can kind of just take that power n out of the function, or out of the limit, sorry. And then kind of from these, we can also derive a few properties about constants. So constant multiplication, we can just take the constant out of the limit, as we can see over here. In this case, beta is just some arbitrary real number. And then if we're taking, the limit of a constant plus a function, or I guess we could also say plus or minus a function, doesn't really matter. And this constant over here, this is just independent of x, right? Because this is a constant, so it's independent of x. Then we can kind of just take it out of the limit, right? Because this isn't, going to change. It's always going to be a constant. So if we wanted to break it down to its separate limits, then it obviously wouldn't change. We can prove these properties, but in general, it is actually quite a simple proof for each of these if you want to think in terms of generalities. And they are very helpful, and you may actually use them without even realizing. So let's go ahead and do a few examples. So let's start with this one over here. The limit as x approaches 3 of x squared minus 3x plus 2. And let me go ahead and use a different color. Let me use red, perhaps. And so essentially, when we're looking at this, we can just use our kind of sum, or sum or difference rule over here. And I mean, we don't really have to sit down and break this up into each of its individual components. We can just kind of look at it and say, okay, we have the x squared, we have the negative 3x, and we have the plus 2. So, I mean, we already know this is going to be a parabola, and we already know when it comes to a parabola, the behavior is kind of uniform. You're just going to have, in both directions, the single-sided limits are going to be equal to each other, so we can just say this is going to be equal to, essentially, this function evaluated at 3. So we would have 3 squared minus 3 times 3 plus 2. And then these two terms would, of course, cancel, so we're just going to be left with positive 2 as our limit. So this one was quite easy, actually. And then let's consider this one over here. The limit as x approaches pi over 2 of 7 times tangent of x. It may be helpful to rewrite this a little bit, so we can, first of all, take the 7 out, so we get 7 times the limit as x approaches pi over 2. And then tangent of x, of course, we know is sine of x over cosine of x. And then you can consider the individual limits, right? This would be 7 times the limit as x approaches pi halves of sine of x. I don't know why that looks like a star. It's not a star. And then the same thing over here, but for cosine of x. And then when we're looking at it this way, we have, okay, sine of x, again, it's this uniform sine wave. This thing is just going to approach, so this will just be 7 times, this limit over here is going to evaluate to 1, right? Because if you're thinking in terms of the sine wave, or thinking in terms of the unit circle, the single-sided limits are both going to approach the same value as x approaches pi over 2. So we can write this as 7 times 1 divided by this limit down here. Now, when it comes to cosine of x, we have to consider, of course, it is also the uniform wave, and we are going to approach the same value. So the single-sided limits do approach the same, well, quote-unquote value, we should say. But we have to keep in mind that this is going to be equal to 0, right? Because we know that cosine of pi halves is, in fact, equal to 0. So here we're dividing by 0. And this entire thing kind of just breaks down, and we had the initial condition that this limit down here in the denominator can't be equal to 0. So this way we can go ahead and say that this limit does not exist. Does not exist. Because we're dividing by 0, of course. And I mean, graphically, if you want to look at this is just going to be a vertical asymptote at x equals pi over 2. So this limit does not exist. And that's kind of how we can actually determine it from the equation. If we get some sort of weird, I suppose, equality that breaks math where we're dividing by 0, then we can just assume that it doesn't exist, right? And there will be particular cases where we could have 0 over 0, and then we can use a rule we're going to kind of look into later on to actually evaluate limits that supposedly don't exist. But as of right now, we can just say this doesn't exist. And then let's look at this last one over here. This one is a nice one as well. Again, if you would like to, we can break it up to its individual components. So we'd have the limit as x approaches e of the natural log of x, and we're going to divide that by the limit as x approaches e of x squared. And then, again, just looking at the individual limits, natural log of x, when x approaches e, we can just determine it graphically. Both the one-sided limits are going to be equal to each other. They're going to approach the same value, which is just going to be the natural log of e. And then same thing with x squared, right? This is just your parent function parabola. We're going to approach the same value from the single-sided limits. And so in this case, we're just going to be approaching some irrational number e. So we would get, or e squared in particular, I should say. And then the natural log of e, we know this is just going to be equal to 1, right? So this is just going to be 1 over e squared. So it's not a very nice number, however, it is still a limit. So this limit does exist, and it is, in fact, 1 over e squared. And so we can just see over here from these 3 examples. I mean, this one was quite simple. This one didn't exist. This one took a little bit more work, but it is also quite nice. But we can kind of just use these properties over here without even realizing it. Like, we used many different properties just kind of naturally, because these are all very intuitive properties. They're very easy to apply, and they certainly make a lot of sense, and they're very easy to kind of derive if you want to think about it that way. So this is essentially just the properties of limits, and we will eventually start exploring kind of further in depth how we can determine discontinuities based on a limit not existing. So that will be for a future video.